Continuation of the previous video about circulation. We just learned about neutrophils, then about monocytes. Monocytes are the largest of all leukocytes. They are granulocytes with a large oval or bean-shaped nucleus which stains with basic dyes. Monocytes are actively phagocytic and they ingest and digest foreign particles such as bacteria just as neutrophils. They also migrate to inflammatory tissues in large numbers. Monocytes are believed to undergo breakdown and release substances called triphons, which stimulate nutrition, cell division, growth, and repair. Triphons. Monocytes account for 4 to 7% of the leukocytes. Their abnormally high number is called monocytosis, and abnormally low number is called monopenia. Monocytosis is usually associated with typhoid fever, malaria, tuberculosis, Rocky Mountain spotted fever, etc. Then lymphocytes. These are the granular leukocytes with very large and DNA-rich nucleus and small amount of clear cytoplasm. They are the second most numerous leukocytes next to neutrophils. They comprises 25 to 35% of leukocytes. Lymphocytes are almost rounded cells with a small quantity of cytoplasm. They are found in all tissues except those of central nervous system. They have a highly variable lifespan of 2 to 200 days. They explain only a slight degree of amoeboid movement and have little phagocytic activity. Some lymphocytes are believed to disintegrate and release triphons. Triphons are nothing else but substances which can stimulate nutrition, cell division, growth, and repair. Okay, so lymphocytes often release triphons. Then lymphocytes are actively involved in immune mechanisms. There are two major classes of immunologically active lymphocytes, namely B lymphocytes and B cells, and T lymphocytes or T cells. B cells secrete antibodies which neutralize antigens. T cells secrete powerful toxins called lymphokines which destroy antigens or kill pathogens. Abnormally high count of lymphocytes is called lymphocytosis and abnormally low count is called lymphopenia. So lymphocytosis is often associated with whooping cough, severe malaria, syphilis, Hodgkin's disease, progressive enlargement of lymph glands. Abnormally high count. Okay. So functions of leukocytes: body defense by lymphocytes, monocytes, and neutrophils. Lymphocytes produce antibodies and lymphokines to fight antigens. Monocytes and neutrophils destroy invading bacteria either by phagocytosis or by releasing the antibacterial enzyme lysozyme. Sometimes some phagocytes squeeze out through the minute pores of blood vessels and come to stay in the intracellular fluid and lymph. This is called diapedesis. In the new sites, they destroy infectious microorganisms by phagocytosis. Release of triphons by the breakdown of monocytes and some lymphocytes to stimulate cell division, growth, and repair in tissues. Eosinophils act against allergens, substances which cause allergic responses, production of heparin by basophils in liver, scavenging of cellular debris, dead bacteria, and other particles by phagocytosis by phagocytes, wound healing and scar formation at healed wounds. Next is about platelets. Blood platelets are the colorless, non-nucleated and irregular corpuscles. They are the smallest of all corpuscles. Their average total count is 200,000 to 400,000 per cubic mm of blood. Platelet count usually decreases using exercise, after meals, during convalescence from infections, and also in hemorrhage, allergic reactions, myeloid leukemia, Hodgkin's disease, etc. Similarly, it falls low in acute infections, irradiation, pernicious anemia, anaphylaxis, etc. Platelets are formed in red marrow by the fragmentation of the parent cells, megakaryoplasts. Their average lifespan is 5 to 9 days. The abnormally high count of platelets is called thrombocytosis, and their abnormally low count is called thrombocytopenia. Spontaneous blood clotting may occur in the former, and clotting may become much delayed in the later. And functions of platelets play an active role in blood coagulation, clotting of blood at injuries by releasing thromboplastinogen and thromboplastinogenase, which are essential for blood clotting. Then bring about homeostasis. Homeostasis is the control of bleeding. It occurs when blood vessels are punctured and slight bleeding follows. During this, the platelets physically stick to the cut edges of vessels in large numbers. This forms a hemostatic plug or platelet plug. It seals up the cut edges of the vessels and prevents bleeding in about 3 to 5 minutes after the injury. The time required for the cessation of bleeding from a small puncture is called a bleeding time. Platelet plug will be formed in that site, hemostatic plug. Then defend the body by clumping over invading microorganisms and foreign particles in huge numbers. Help vasodilation, dilation of blood vessels by releasing histamine and serotonin. Then general functions of blood. The important functions of blood, human blood, are the following: transport of nutrients from stomach, intestine, and liver tissues, transport of respiratory gases O2 and CO2 between lungs and tissues, transport of metabolic wastes and toxins from tissues to kidneys and sweat glands. Then transport of hormones from their sources, endocrine glands, to target sites, action sites, transport of enzymes from exocrine glands to cells, transport of metabolites among and between tissues. So, supply of necessary substances to secreting glands, defense against infections and toxins, regulation of body temperature by absorbing, releasing, and distributing heat, maintenance of a proper and constant body pH, acid-base balance through buffering actions, maintenance of water balance in cells by transporting excess water to kidneys and sweat glands, and regulation of electrolyte balance and fluid balance by removing salts from tissues to kidney. Once again, I'm going to read this. General functions of blood. The important functions of human blood are the following. Earlier, we learned functions of platelets, which play an active role in blood coagulation, bring about hemostasis, defend the body, help vasodilation. General functions of blood: transport of nutrients from stomach, intestine, and liver to tissues, transport of respiratory gases between lungs and tissues, transport of metabolic wastes and toxins from tissues to kidneys and sweat glands, transport of hormones from their sources to target sites, transport of enzymes from exocrine glands to cells, transport of metabolites among and between tissues. Some other aspects related to the supply of necessary substances to secreting glands, then defense against infections and toxins, regulation of body temperature by absorbing, releasing, or distributing heat, maintenance of a proper and constant body pH or acid-base balance through buffering actions, maintenance of water balance in cells by transporting excess water to kidneys and sweat glands, then regulation of electrolyte balance or fluid balance by removing salts from tissues to kidneys. Then is about clinical analysis of blood. The study of the constituents of human blood through clinical analysis or chemical examination is known as hematology. The clinical analysis of blood is significant in that it provides valuable clues for the diagnosis of several diseases. The common hematological investigations carried out in routine medical examinations include the determination of complete blood count (CBC), total blood count (TRC), and total leukocyte count (TLC), and determination of differential leukocyte count, and the estimation of erythrocyte sedimentation rate, lipid profile, hemoglobin content, blood glucose level, and blood urea level. Apart from this, vital test is done for the diagnosis of enteric fevers and ELISA test for the diagnosis of AIDS. First, hemocytometry and hemocytometer. Hemocytometry is the counting of the corpuscles of circulating blood. It is done either manually or by using automated systems. Manual method is laborious, time-taking, error-prone, and less reliable, but still this method is conducted in various, classroom settings, just for practice and to increase concentration, whatever it may be, just increase the skills used for operating microscope or something else, something like that. So on the other hand, automated method is easy, almost error-free, and most reliable, but it may require some systems. The instrument used in manual counting of blood corpuscle is called hemocytometer. A hemocytometer set consists of special type of rectangular glass slide called counting chamber, a special type of cover glass, a special type of diluting pipette called micropipette, and a stylet to clean the diluting pipette. Stylet. Okay. Counting chamber. Burke's hemocytometer. Micropipette will be there. Improved Neubar counting chamber, depth 0.1 mm. Ruled area counting chamber, left upper block. Just imagine a square rectangle. Its four corners are once again divided into many short columns. If you need more understanding about this structure, just Google this picture of hemocytometer. So hemocytometer contains 1 mm length into 1 mm length breadth portion, left upper block, then right upper block, then left lower block, and left right lower block. These four regions are there, and in the middle there will be another region. So counting chamber is a thick rectangular glass slide with etched areas for counting blood corpuscles. Different types of counting chambers are in use. The most commonly used type is the improved Neubar counting chamber. On its upper side are two depressed and ruled areas bordered by deep moats. These depressed areas are called counting areas. They are used for counting the number of corpuscles present in a given area. On the upper side are two depressed and ruled areas bordered by deep moats. These depressed areas are called counting areas. They are used for counting the number of corpuscles present in a given area. When a cover slip is placed over the counting area, a space will be left between its lower surface and the bottom of the counting area. This is called the depth of the counting chamber. The depth of improved Neubar counting chamber is 0.7 mm. In this chamber, each counting area is ruled in such a way that it is divided into numerous squares. Each ruled area is 9 mm square and is divided into 9 large squares. Of this, the 4 corner squares are used for counting, while white corpuscles and the centered square is used for counting red corpuscle. Each corner square is further divided into 16 smaller squares. Similarly, the central square is at first divided into 25 smaller squares, each of which is further divided into 16 still smaller squares. So 1 by 20 into 1 by 20 squares. So the area of the ultimate or smallest square is, since the counting chamber is deep, the actual volume of each of the square is 0.00025 cube. And micropipettes are used for diluting the sample blood. A micropipette has 3 portions, namely a narrow graduated stem, and expanded bulb, and a rubber tube. Bulb is the middle part in which the sample blood gets mixed with the diluting fluid. It contains a plastic head or beads which facilitate the thorough mixing of blood with the diluting fluid. It also prevents the entry of air bubbles. A rubber tube is used for aspirating the sample blood and the diluting fluid. There are 2 types of micropipettes usually RBC pipettes and WBC pipettes. Both are similar but with minor variations. The bulb of the WBC pipette is slightly smaller than that of the RBC pipette. The stem of the RBC pipette bears the marking 0.1 and 0.5 and 1 before the bulb and not 101 after the bulb. On the other hand, the stem of the WBC pipette begins the marking 0.5 and 1 before the bulb and 11 after the bulb. Diluting fluid. The diluting fluid is used for RBC counting is different from that used for WBC counting. The most commonly used fluid in RBC counting is Hem's fluid, HAYEM solution. Thus, its composition is as follows: NaCl 1 gram, Na2SO4 5 gram, HgCl2 corrosive sublimate 0.5 gram, distilled water 200 ml. Another solution is frequently used as the composition: sodium chloride 0.6 gram, sodium citrate 1 gram, formalin 1 ml, and distilled water 100 ml. The diluting fluid commonly used in WBC counting is Turk's fluid, TUERKS fluid. It is the following composition: glacial acetic acid 2 ml, 1% gentian violet solution, 1 ml distilled water 97 ml. Glacial acetic acid hemolyzes RBCs, leaving the WBCs intact. WBCs will be intact. At the same time, gentian violet stains the nuclei of WBC, making them more prominent for the easy determination and counting. Often, the small quantity of thymol is added to the diluting fluid to prevent fungal growth. Then, procedure of blood cell counting. In blood cell counting, the sample blood is first diluted in the micropipette using the appropriate diluting fluid. In the diluted blood is then transferred to the counting chamber. This is called charging. The diluting fluid is then transferred to the counting chamber. This is called charging. During this, the counting chamber is placed on a flat surface and blood is charged into it at an angle of 40 degrees Celsius, avoiding air bubbles and excess spillage. The counting chamber is then covered with cover glass. The whole setup is kept undisturbed for nearly 5 minutes for settling of cells. Then count the cells in the respective areas with the help of a microscope. Usually low power objective is used for counting WBC, and high power objective is used for counting RBC and platelets. Finally, by making use of data regarding number of cells counted, the area covered in counting, the dilution of the blood, and the depth of the counting chamber, the number of cells present per cubic mm of blood is determined by applying the formula. Cell per mm cube of blood is equal to n into diluting factor into depth factor by area covered. N represent total number of cells counted. Total leukocyte count, TLC. Leukocytes are the colorless amoeboid and nucleated blood cells. The total number of leukocytes per cubic mm of blood is called TLC. In a normal healthy human being, it ranges between 5,000 and 8,000 per cubic mm of blood. TLC is determined with the help of hemocytometer. The major requirement for this include blood sample and appropriate WBC diluting fluid. WBC diluting fluid in the sense Turk's fluid. Then WBC pipette, which contain a small bulb, then counting chamber with cover glass. The most commonly used diluting fluid is Turk's fluid, 20% acetic acid, and the commonest counting chamber is improved newborn counting chamber. In TLC determination, a known volume of the sample blood is drawn up using the micropipette. It is then diluted to a known quantity with the diluting fluid and charged or filled into the counting chamber. The whole setup is kept undisturbed for nearly 5 minutes for the settling of cells. The diluting fluid hemolyzes and removed RBC, enabling the counting of leukocytes. If the diluting fluid is colored, it will stain the nucleus of WBC, making their detection very easy. Finally, the settled leukocytes are counted using the low power objective of a microscope. The total number of leukocytes per mm square cube of blood is worked out by applying the formula number of cells counted into dilution factor into depth factor by area covered. Number of cells counted, dilution factor into depth factor by area covered. Abnormal variations often occur in the total count of leukocytes. Abnormal increase is called leukocytosis, and abnormal decrease is called leukopenia. Leukocytosis and leukopenia. These variations may be due to physiological or pathological reasons. The physiological factors which raise the TLC include menstruation, pregnancy, high muscular activity, high temperature, etc. The physiological factors which decrease TLC is old age. The pathological factors which increase TLC is viral and bacterial infections, parasitic invasion, leukemia, tumors, heart disease, etc. The pathological factors which decrease TLC are viral, bacterial and protozoan infections, liver cirrhosis, rheumatoid arthritis and radiations. Then differential leukocyte count, DLC. DLC is something which is conducted to differentially count all these leukocytes. So DLC is the percentage or proportion of the different kinds of leukocytes in the peripheral blood. Leukocytes are of 5 different kinds, namely basophils, neutrophils, eosinophils, lymphocytes, and monocytes. Determination of DLC is completed in 3 steps, namely preparation of blood smear, staining of the smear, and microscopic microscopic examination of the smear. Blood smear is a thin film of blood on a microscopic slide. For this preparation, capillary blood is collected by skin puncture. Then a large drop of blood is placed near one end of a clean slide. Soon it is spread uniformly all over the slide with the head of another slide called a spreader slide. The spreader slide is first held in a slanting position at an angle of 30 to 40 degree. One end of it touching the other side just in front of the blood. Soon it is moved backward to the blood. Blood flows to its edge. Then it is moved forward so that thin film of blood is left over the slide. The smear is then dried on air and carefully stained using a standard stain. Leishman stain, Ritz stain, Jenner stain, etc. The stained slide is then washed, dried, and observed under microscope using the low power objective. WBCs appear pink colored, platelets appear deep violet, and nucleus of leukocytes are stained purple. The different types of leukocytes are distinguished on the basis of characteristic form of their nucleus. RBCs appear pink colored, platelets appear deep violet, and nucleus of leukocytes are stained purple. Differential counting of leukocytes can be done in different ways. In one method is done to and fro from end to end in the lengthwise direction. In another method, it is done to and fro from edge to center in the breadthwise direction. In any case, a minimum of 100 cells are counted. While counting, the number of each type of leukocytes is noted, and based on this data, the percentage of the differential types are calculated. The normal proportion of leukocytes is as follows: basophils, neutrophils, eosinophils, lymphocytes, monocytes, like that. Basophils 0.5 to 1%, neutrophils 60 to 70%, eosinophil 2 to 4%, lymphocytes 20 to 40%, monocytes 3 to 8%. So basophils are very minute and are not that much present. Then abnormal variations in DLC are observed under abnormal conditions. Some of such abnormalities are given below. Basophilia, increased number of basophils seen in leukemia, hemolytic anemia, chickenpox, etc. Then neutrophilia, increased number of neutrophils observed in pneumonia, appendicitis, leukemia, tonsillitis, etc. Then neutropenia, decreased number of neutrophils observed in lymphoid, typhoid, parathyroid, typhoid, malaria, measles, mumps, etc. Then eosinophilia, high number of eosinophils observed in allergic diseases such as asthma, hay fever, eczema, etc. Lymphocytosis, increased number of lymphocytes observed in measles, mumps, whooping cough, etc. Lymphocytopenia, decreased number of lymphocytes observed in leukemia, heart disease. Monocytosis, high number of monocytes observed in malaria, tuberculosis, typhus fever, etc. Then erythrocyte sedimentation rate, or ESR. ESR, or suspension stability, is the rate at which erythrocytes settle down in a vertical column of anticoagulated blood. This is the test for measuring the activity and progress of certain diseases. If blood is drawn and kept in a vertical test tube, RBCs sink, leaving a clear layer above. The rate of this sedimentation varies with physiological and pathological conditions. It is high in disease and is directly proportional to the intensity of the disease. Clinically, ESR is determined by several methods such as Westergren's method, Cutler's method, Landau's method, and Winthrop's method. Of this, the first one is the most commonly used method. Which one? Westergren's method. Its requirements include a Westergren's pipette fixed on a stand, an anticoagulant, and a blood sample. The anticoagulant is 3.8% of sodium citrate solution prepared by dissolving 3.8 grams sodium citrate in 100 ml of distilled water. In Westergren's method, the sample blood is first mixed with the anticoagulant with the ratio 4:1. The mixture is then filled into the vertical pipette till its level reaches the 0 point mark. The whole setup is allowed to remain undisturbed for 1 hour at room temperature. After 1 hour, note the level of the blood column. It can be observed that red corpuscles settle down as a result of Rolex formation. Rolex is a heap into which RBCs collect. RBCs move about randomly in the plasma. During this movement, they collide with each other and stick together, forming Rolex. This stickiness is due to the presence of protein molecules. Once Rolex is formed, its density and specific gravity increase and it sinks down quickly. Thus, ESR depends mainly on the factors which govern Rolex formation. They include the albumin, globulin, fibrinogen, and lipid contents of plasma, shape and size of RBCs, and number of RBCs. The normal ESR value is a little lower in males than in females. It will be still lower in children and much higher in old age. The normal ESR value is as follows. At the end of one first hour, male 3 to 5 mm, female 4 to 7 mm. Then in Trope's method, at the end, ESR is not a diagnostic test for any disease, but rather a pro-diagnostic test. A raise in ESR value in 2 consecutive tests with an interval of 1 hour indicate increased activity of disease. Thus, a change in ESR is more important than its actual value in the detection of presence of a disease. However, it does not indicate the exact nature of the disease. Abnormal variations in ESR are often observed in following psychological and pathological conditions. Increased ESR observed in pregnancy, menstruation, patrician, rheumatic fever, tuberculosis, malignancy, pneumonia, anemia, administration of vaccines, etc. Then reduced ESR observed in newborn babies, congestive heart failure, polycythemia, congenital absence of fibrinogen, congenital spherocytosis, spherical shape of RBC. Then reduced ESR is observed in newborn babies, congestive heart failure, polycythemia, congenital absence of fibrinogen, congenital spherocytosis, spherical shape of RBCs. Then estimation of blood glucose. In the biochemical analysis of blood, the levels of blood glucose and blood urea are estimated using colorimetry. Colorimetry is the analysis based on the comparison of the color intensity of a sample solution of the unknown composition of that of a standard solution of known composition. The apparatus used in colorimetry is known as photoelectric colorimeter. Estimation of blood glucose is done as a routine test for the diagnosis and management of diabetes mellitus. Several methods have been employed for this purpose. Old methods are based on the reducing property of glucose. Glucose is a reducing sugar by virtue of the presence of aldehyde group, and it can reduce cupric oxide to cuprous oxide in an alkaline medium. Hole and Wu method, orthotoluidine test, Nelson, Somogyi method, King method, etc. are old methods. So Folden and Wu method, this is an old method of glucose estimation. It is based on the principle that when protein-free and sugar-containing blood filter, it is heated with alkaline copper solution, cupric salt gets reduced to cuprous salt. In Folden Wu method, the blood sample is first heated with alkaline copper tartarate. Blood glucose reduces copper to cuprous oxide. Cuprous oxide in turn reduces phosphomolybdenic acid to phosphomolybdous acid or molybdenum blue, which makes the solution blue colored. The color intensity is directly proportional to the glucose content of the blood. It is measured using colorimeter and compared with that of similarly treated standard sugar solution to estimate the glucose content. Then an abnormally high blood sugar level is called hyperglycemia. It is an indication of diabetes. Abnormally high blood glucose level is called hypoglycemia. Then modern methods. Old methods of glucose estimation are not specific and their results are not accurate. The reason is that certain other substances such as fructose, galactose, urea, uric acid, creatinine, etc. also have reducing properties and they often interfere with the results. The only specific method of glucose estimation is the enzymatic method. It gives accurate result. It is of two types, namely glucose oxidase peroxidase method and exokinase method. In the former, glucose is first oxidized by using the enzyme glucose oxidase. This produces hydrogen peroxide and gluconic acid. Hydrogen peroxide is soon split into oxygen and water using the enzyme peroxidase. Oxygen is made to react with an oxygen acceptor to produce a red colored solution. The relative intensity of the color is directly proportional to the glucose content. The glucose content can be estimated colorimetrically by using photoelectric colorimeter. An estimation of blood urea by oxime method. Blood plasma contains different metabolic wastes, of which urea is most important. The commonest method of estimation of blood urea is the oxime method, modified diacetyl monoxime thiosemicarbazide method. In this method, blood urea is made to react with diacetyl monoxide and acidic solution of thiosemicarbazide in the presence of Fe3+ or cadmium ions. This gives a pink color. It is due to the formation of dioxime derivatives. The intensity of coloration is directly proportional to the urea content of the blood. It is measured colorimetrically and compared with standard coloration. Normal blood urea levels of a fasting person is between 10 and 40 mg per 100 ml of blood. But when the kidney is not functioning properly, glomerular ultrafiltration will not be proper. This leads to an increase in blood uremia. So, an increased level of blood urea indicates kidney disorder. Then estimation of hemoglobin. The hemoglobin content of human blood varies with age, sex, and physiological conditions. An increased content is noticed when blood gets concentrated due to acute loss of water and also when the number of RBC goes very high, as in high altitudes. Decrease in hemoglobin content is often associated with anemia conditions. So, estimation of hemoglobin is usually done with the detection of anemia. There are several methods of hemoglobin estimation, such as physical, specific gravity methods, chemical method, then colorimetric method. Of this, colorimetric methods gives accurate result. So, colorimetric methods are based on the preparation of intensity of color of hemoglobin of its derivatives in a given blood sample with standard coloration. Colorimetric methods are of two kinds, namely visual colorimetry and photoelectric colorimetry. Acid Hamilton method of visual colorimetry is a commonly employed method. So, visual colorimetry, acid Hamilton method. Acid Hamilton method involves the conversion of hemoglobin to acid Hamilton by the action of an acid. Acid Hamilton is brown colored. The intensity of the brown color depends upon the amount of the acid Hamilton formed, which in turn depends upon the hemoglobin content of the blood. Sally's method is the simplest acid Hamilton method. In Sally's method of visual colorimetry, the blood sample is treated with 0.1 normal HCl. Hemoglobin is converted to brown colored acid Hamilton. The intensity of the brown color is directly proportional to the amount of hematine, which in turn is proportional to the hemoglobin content of the blood. The solution is then diluted until this color matches with the color of the standard solution. From the extent of the dilution required for matching the color, the quantity of hemoglobin can be calculated. The hemoglobin content of blood is expressed in gram per 100 ml of blood, gm percentage. The normal value in male is 14 to 18 gm percentage. Female is 12 to 16 gm percentage and a newborn baby is 20 to 25 gm percentage. The apparatus used for the estimation of hemoglobin or visual colorimetry is hemoglobinometer or hemometer. The commonest one used in the colorimetric estimation of hemoglobin is Sally's hemoglobinometer. Then photoelectric colorimetry. Cyan methane hemoglobin method. The commonest method of photoelectric colorimetry in hemoglobin estimation is the cyan methemoglobin method. In this method, hemoglobin is converted to cyan methemoglobin using Dubkin's reagent, which contains sodium bicarbonate, potassium ferric cyanide, and potassium cyanide. At first, potassium ferric cyanide of the reagent oxidizes the iron part of hemoglobin from ferrous to ferric state, forming methemoglobin. Methemoglobin now reacts with cyanide ions of potassium cyanide and forms cyan hemoglobin. The intensity of the color of cyan methemoglobin is directly proportional to its quantity, which in turn is directly proportional to the hemoglobin content of the blood. Using photoelectric colorimeter, the amount of cyan methemoglobin can be measured, and based on this value, the quantity of hemoglobin can be estimated. Then lipid profile. Lipids are essential constituents of blood plasma and also the structural framework of all cell membranes. In blood plasma, they exist mostly as lipoproteins. The concentration of the different kinds of lipids in blood plasma is called a lipid profile. Lipoproteins are tiny micellar spherical particles visible only through an electron microscope. The lipoproteins of human blood can be separated by ultracentrifugation. Based on their sedimentation coefficients in ultracentrifugation, they can be classified into several groups such as high density lipoprotein or HDL, then low density lipoprotein or LDL, and intermediate density lipoprotein or IDL. Very low density lipoprotein or VLDL, chylomicrons, etc. In addition to this, cholesterol, phospholipids, etc. also form a part of lipid profile. Chylomicrons are protein-coated particles of triglycerides and very small quantity of cholesterol. Density of lipoproteins and phospholipids depends on the quantity of the lipids present in them. VLDL has only very little of lipids and HDL has a high percentage of lipids. The clinical estimation of the various lipoprotein constituents of blood plasma is usually done after night fasting. An analysis of lipid content of blood plasma is very important because high lipid levels in blood are the major reasons for several cardiovascular problems. For example, high blood cholesterol level, hypercholesterolemia is a major contributing factor for atherosclerosis, hardening, thickening, and narrowing of blood vessels, arterial blocks, ischemic heart diseases, stroke, etc. The normal lipid profile is important. Phospholipid 150 to 200 mg, triglycerides 75 to 150 mg, cholesterol 50 to 100 mg, HDL in males 30 to 60, in females 35 to 75 mg, LDL age 15 to 30 years 50 to 150 mg, age 30 to 40 years 75 to 180 mg, age 40 to 60 years 90 to 200. And coagulation of blood. Coagulation or clotting of blood is the conversion of fluid part of blood to a thick jelly known as clot or thrombus. So coagulation or clotting of blood is the conversion of the fluid part of the blood to a thick jelly known as clot or thrombus. Normally, clotting takes place when blood sheds out from injuries or wounds. The solid clot seals up the broken tips of blood vessels and prevents further bleeding and loss of blood. Thus, coagulation of blood is a major chemical defense against the loss of blood through injuries or wounds. The yellowish or straw-colored liquid that oozes out from the clot is called serum. It is simply blood plasma without of its clotting proteins. Then coagulation factors. Blood clotting involves a large number of biochemical agents known as coagulation factors or clotting factors. They include 12 plasma coagulation factors, 4 platelet coagulation factors, and a tissue coagulation factor, which is a member of the plasma factors. The major coagulation factors and their respective roles are given in the table in the page after the text. We will be reading that. Then coagulation of blood is the net result of complex series of enzymatic reactions. These reactions are completed in 3 major stages as follows. Formation of the active enzyme thromboplastin from the inactive enzyme thromboplastinogen with the help of active factors. So thromboplastinogen activating factors thromboplastin. Then conversion of the plasma protein prothrombin or thrombogen into the active enzyme thrombin with the help of thromboplastin, several plasma coagulation factors and Ca2 plus ions. Prothrombin to thrombin with the help of thromboplastin and Ca2 plus plasma factors. Then conversion of soluble plasma protein thrombinogen into insoluble fibrin with the help of thrombin. Fibrin forms the thread of the clot. It forms a loose lacework in which blood corpuscles get entangled, forming the final clot. So fibrinogen, thrombin, fibrin thread. Then biochemical pathways of coagulation. Enzyme cascade theory. Blood coagulation is the net result of a complex series cascade of enzyme catalyzed biochemical reactions called enzyme cascade systems. Enzyme cascade mechanisms involve two distinct routes, namely extrinsic pathway and intrinsic pathway. In the former, thromboplastinogen is released from the damaged tissue cells, but in the later it is released by the breakdown of blood platelets. These two pathways later on merge together. Then extrinsic pathway. The extrinsic pathway of blood coagulation begins with the release of lipoprotein extrinsic thromboplastinogen plastinogen or tissue thromboplastinogen from the ruptured part of the blood vessels or from the damaged tissue around. So thromboplastinogen reacts with the clotting factors and gets transformed to active thromboplastin or extrinsic thromboplastin. This conversion represents the first stage of coagulation. The second stage of extrinsic pathway involves the conversion of blood proenzyme prothrombin, that is thrombogen, into the active enzyme thrombin. Prothrombin is produced and released by liver. It reacts with extrinsic thromboplastin and the plasma clotting factors. In the third stage of extrinsic pathway, the plasma contained fibrinogen gets transformed to insoluble fibrin by reacting with thrombin and the plasma clotting factors. Fibrin is a loose meshwork of interlacing strands. It is converted to a tight and dense aggregate by the formation of covalent crosslinks between the strands. This reaction is catalyzed by the clotting factors. Intact fibrin network forms the clot. In the meshes of fibrin network, blood corpuscles get entangled and forming a jelly-like plug which forms the final clot. This plug seals up the broken blood vessel and prevents further loss of blood. From the clot, a clear yellow liquid oozes out. This is called serum. This is the blood plasma from which fibrinogen is removed for clotting. N is about intrinsic pathway. The intrinsic pathway of blood clotting begins with the adherence of numerous blood platelets to the ruptured area of blood vessel. This clumping together of platelets close their disintegration, releasing the platelet coating factors to the blood plasma. In small injuries, platelet clumping deals up the injury without initiating the clotting reactions. Then the first stage of intrinsic pathway involves the conversion of inactive intrinsic thromboplastinogen to activate intrinsic thromboplastin. In this case, thromboplastinogen reacts with the plasma clotting factors and the platelet clotting factor PF1, PF2, PF3 and PF4. In the second stage, prothrombin gets converted to thrombin by reacting with intrinsic thromboplastin and plasma factor 4, 5, 6 and 8, 10. In the third stage, fibrinogen are converted to fibrin by reacting with the thrombin and plasma factors and platelet factor PF2. Initially, fibrin forms a loose meshwork over the injured part. It is soon stabilized to dense network by the action of plasma factors in the extrinsic pathway. Apart from converting fibrinogen to fibrin, thrombin stimulates the clumping and disintegration of more and more platelets, releasing still more platelet factors. This is a kind of positive feedback and it ensures continuous platelet disintegration until the final clot is formed. Then anticoagulants. Anticoagulants are the chemical substances which can prevent blood clotting. Naturally occurring biological anticoagulation include heparin, plasmin, thrombomodulin, antithrombin, protein C, hirudin, snake venom, etc. Synthetic anticoagulants include synthetic heparin, coumarin, and oxalates and citrates of sodium and potassium. Salicylate, citrate phosphate, then dextrose, acid citrated dextrose, ethylene diamine tetraacetic acid. Synthetic anticoagulants are used in laboratories and blood banks for preserving blood. These chemicals react with Ca++ and form insoluble compounds. So blood Ca++ is no longer free to catalyze the conversion of prothrombin to thrombin. So dicumarole and other pharmaceutical preparations for preventing blood clotting. And heparin is a quick-acting anticoagulant which checks blood clotting mainly by preventing the conversion of prothrombin to thrombin. It is produced by liver cells and mast cells of connective tissue. Heparin is a mucopolysaccharide. Its anticoagulant property results from its strong electronegative acidic group. It inhibits the clumping and disintegration of platelets, activation of thromboplastinogen to thromboplastin, conversion of prothrombin to thrombin, and the thrombin-fibrin interaction. Then plasmin is a natural anticoagulant which circulates the blood in inactive plasminogen. It serves as an anticoagulant by degrading fibrin and fibrinogen. Then thrombomodulin. Thrombomodulin is a membrane-bound glycoprotein found in the endothelial lining of blood vessels. It serves as an anticoagulant by binding and inactivating thrombin. Inactivated thrombin is no longer capable of forming clot. Then antithrombin. Antithrombin is a plasma globulin. It serves as an anticoagulant by neutralizing some clotting enzymes and clotting factors and also by inactivating thrombin. And protein C, hirudin, snake venom. Hirudin is a strong anticoagulant found in the saliva of blood-sucking leeches. It is antithrombin in action and interferes with the action between thrombin and fibrinogen. Then snake venom, the venom of cobra. Some species of vipers are powerful anticoagulants by virtue of their anti-thromboplastin property. So they interfere with the conversion of prothrombin to thrombin. Then hemostasis. Hemostasis is the control or stoppage of bleeding from cut, damaged or injured blood vessels. It involves three successive mechanisms, namely successive spasm, plateletic plug formation, and coagulation. These mechanisms are useful to prevent hemorrhage only in a smaller blood vessels. Then vascular spasm is the constriction of the damaged blood vessel by the kick and spontaneous contraction of the smooth muscle of its wall immediately after the damage. It reduces blood loss up to 30 minutes. During this time, other hemostatic mechanisms can go into operation. Molecular spasms probably result in the reflexes initiated by the pain receptors and also from the stimulation of the vasoconstrictor serotonin released by the blood platelets. So platelet plug formation, blood platelets play an important role in hemostasis. Soon after vascular spasm, they get activated by thrombin and come into contact with the cut or damaged edges of the vessel. Soon they enlarge in size, become irregular and sticky, and stick to the collagen fibers or endothelium of the gut edges of the vessels. This forms a loose platelet patch. The activated and attached platelets release ADP and some enzymes which attract other platelets and cause them to stick to the platelet patch. This platelet clumping is stimulated by fibrinogen. The accumulation and attachment of platelets in large numbers form a tight temporary clot in about 5 minutes after the injury. This is called the hemostatic plug or platelet plug. It seals the break in the vessel and prevents the loss of blood. Then coagulation, the hemostatic plug is soon strengthened and stabilized by the formation of fibrin mesh over and around it. It is called clot or thrombus. If the thrombus contains platelets alone, it is called white thrombus. Sometimes erythrocytes also get attached to the platelet plug. Such a thrombus is called a red thrombus. Once bleeding has come to complete halt, the clot is dissolved by the action of an enzyme called plasmin. That is called fibrinolysis. Plasmin exists in the plasma blood as an inactive precursor of proenzyme called plasminogen. It is activated by proteolytic enzymes such as trypsin. And next topic is about hemolysis and jaundice. Hemolysis is the breakdown or rupture of plasma membrane of RBC and the consequent release of hemoglobin. Massive hemolysis in all probability may cause a form of anemia called histolytic anemia. Hemolysis can occur for various reasons such as the presence of hemolysin and toxic chemicals, snake poisoning, mechanical destruction, osmotic shock, incompatible blood transfusion, malaria, then glucose 6-phosphate dehydrogenase deficiency. It's a genetic disorder. And hemolysin is an antibody that can activate a complement system to cause the lysis of RBC. Hemolysis is common in pernicious anemia and it occurs very rapidly in poisoning by hemotoxic snake venom. Then hemolysis causes three serious disorders, namely hemolytic anemia, erythroblastosis fetalis, hemolytic disease of newborn, then and hemolytic jaundice. Hemolytic anemia results from excessive hemolysis and consequent steep fall in RBC count and hemoglobin content of the blood. If it is due to the high fragility of RBC, it is called congenital hemolytic anemia. Then erythroblastosis fetalis is a severe form of hemolysis that results from maternal fetal Rh incompatibility. In this case, maternal blood is Rh negative and fetal blood is Rh positive. The Rh positive fetal blood reaches the mother through placental circulation. This causes the formation of anti-Rh antibodies in the blood of the mother. These antibodies then reach the fetus through placental circulation. This causes antigen-antibody reaction in the fetus and massive hemolysis resulting in erythroblastosis fetalis. And is about hemolytic jaundice. Jaundice of or icterus is the yellow discoloration of the skin, mucous membranes, white of eyes, sclera, and body fluids due to excessive deposition of the bile pigment bilirubin. During hemolysis, hemoglobin undergoes degradation in liver and spleen. Its heme portion is transformed to a green pigment called biliverdin. Biliverdin undergoes oxidation and forms the reddish yellow pigment bilirubin. When liver is unable to remove bilirubin from blood because of increasingly high destruction of RBC, large amount of bilirubin circulates through bloodstream and get deposited in tissues. This causes hemolytic jaundice. Sometimes liver fails to remove bilirubin from blood due to the obstruction of the bile duct. This causes obstructive jaundice. Then hepatogenic jaundice. Apart from hemolytic jaundice, there is another type of jaundice called the hepatogenic jaundice. This is a usual type and it results from absorption of bile through blood and lymph and not from hemolysis. Its main cause contains hepatitis, inflammatory disorganization of liver due to viral infection, then cirrhosis of liver, alcoholic liver diseases, obstruction to the flow of bile along the bile channels and bile duct. Obstruction to the flow of bile may be due to some causes inside the liver like gallstones or outside the liver like pancreatic cancer, intestine, it's absorbed intestine, enlargement of the glands inside, lying near the liver. When the bile cannot flow freely into intestine, it's absorbed to blood and lymph, and some of its constituents get deposited in various tissues all over the body. Certain infectious diseases, just like yellow fever, then malaria, typhoid fever, and blood poisoning, in which abscesses appear in various parts of the body, may also cause hepatic jaundice. Acute yellow atrophy of liver is a rare and serious condition accompanied by hepatic jaundice. Next, we are going to learn about some other diseases or hemoglobinopathies. Hemoglobinopathies are genetically determined and race-related hereditary human disorders due to abnormal hemoglobin. They are characterized by impaired formation of normal adult hemoglobin and hemolytic anemia, sickle cell anemia, then cyclemia or sickle cell disease or SCD, and thalassemia are two common hemoglobinopathic disorders. Sickle cell anemia is a severe type of hemolytic anemia in which RBCs are distorted and sickle-shaped. The sickling of RBC is due to the presence of an abnormal hemoglobin called sickle cell hemoglobin or hemoglobin S. This is partly or almost completely replaced the normal adult hemoglobin or HbA. HbS differs from HbA in having valine instead of glutamic acid in the 6th position of one or both of its beta chains. So sickling of the RBC is due to the crystallization of HbS under conditions of low PO2 in veins. This often slows down or obstructs blood flow, resulting in the infarction of the respective tissues. Sickled RBCs are often fragile than normal RBCs and so they rupture very easily. Also, they have only low oxygen binding powers. Their lifespan is very short and they undergo massive destruction in spleen. This causes a fatal type of hemolytic anemia called sickle cell anemia. The clinical symptoms of disease include enlarged spleen, rheumatic ailments, then mental disorders, severe hypoxia, and very rarely cardiac problems and renal failures. Sickle cell anemia is a congenital disease caused by the recessive lethal mutation of an autosomal structural gene which governs the synthesis of the beta chain hemoglobin. It is found among the populations or the descendants of the populations inhabiting the malaria belt around the world. It is common among the Negro populations of Africa and America and also among the peoples of Mediterranean countries. In Kerala, it is prevalent among the tribals of Wayanad. Then thalassemia. Thalassemia, also known as Cooley's anemia or Mediterranean anemia, is a serious disease of the childhood, fatal before puberty. It is an abnormality in the quantity and not in the chemical nature of hemoglobin. The affected persons will have high amounts of fetal hemoglobin HbF, but only very insufficient amount of adult hemoglobin or HbA. This is due to the recessive mutation of the autosomal globin gene. Thalassemia has high frequency among the people of Mediterranean countries, Greek, Italians, Turks, and Spaniards. Spain. So Middle East and Far East, and it's particularly high incidence among Greeks and Italians. The major symptoms of thalassemia include severe anemia, persistent jaundice, enlarged liver and spleen, retarded growth, swollen belly, etc. Severely affected children may die before the age of 10 years. Thalassemia has three major characteristics: continued production of HbF even after birth, much reduced production of HbA, and HbF containing RBCs are minute and abnormal and have only very low oxygen carrying powers. The HbF containing RBCs die much faster and result in a very serious form of anemia. In such cases, periodic blood transfusion or bone marrow replacement is essential to offset the anemia. Thalassemia is of two types, major and minor. The former or the major one is a severe type. and its victims are homozygotes of the mutant G. On the other hand, the later is a mild form and its victims are heterozygotes of the mutant G. In one type of thalassemia, there is extremely insufficient synthesis of alpha genes, both of the fetus and the adult. So it is called alpha thalassemia. On the other hand, there is a extremely low production of beta genes, and so it is called beta thalassemia. Both this can be major or minor depending upon whether the mutant genes exist in homozygous or heterozygous conditions. Next is about transfusion of blood. Blood transfusion is the intravenous transfer or administration of one person's blood to another's body. A person who receives blood is called recipient, and the one who donates blood is called donor. This is some basic information. Nowadays, blood transfusion has become a very common practice to make up extreme deficiency or heavy loss of blood as a treatment for anemia or for giving temporary relief of hemophilia and acute leukemia. At the same time, it is not safe to transfuse blood from all donors without any restrictions to all recipients. This is because the blood of different individuals can be chemically different, and when two different types of blood are mixed together, they may react with each other. Such mutually interacting types of bloods are said to be incompatible or mismatching. Those which do not interact are called compatible or matching types. Transfusion of incompatible blood causes the death of the recipient. This is because the clumping of or agglutination of donor's red corpuscles in the recipient. The clumped RBCs crack and cause toxic reactions fatal to the recipient. Transfusion of mismatching of blood has some more difficulties also. In it, the corpuscles of the donor blood often break up in the new circulation. So also the recipient person may suffer from metal rash, breathing difficulty, and other disease, purging, etc. The immediate destruction of RBC in the recipient may cause jaundice in some cases. The mandatory steps to be taken in precautions in blood transfusions include the typing of the blood donor and the recipient blood to ascertain whether they are compatible with the recipient to A, B, or Rh antigens, and screening of the donor blood to know whether it is infected with human immunodeficiency virus, hepatitis B virus, and malarial parasites, etc. Administration of furosemide to prevent fluid overload of the recipient is at the risk of congestive and heart failure. Next is about agglutination of blood. Agglutination is the clumping together of the red corpuscles of the donor blood in the recipient when blood transfusion occurs in compatible or mismatching types of blood. Agglutination is a result of an antigen-antibody reaction. The antigen is known as agglutinogen and the antibody agglutinin. Agglutinogen occurs in red corpuscles and agglutinin in plasma. Most agglutinins are naturally occurring antibodies, so they are always found in blood. ABO blood system in 19 Carl Landstein recognized four major groups of human blood, namely AB, AB, and O, ABO system. This grouping was made on the basis of two antigens and two antibodies, namely antigen A and B, antibodies small a and small b, anti-A antibody, and anti-B antibody A. Group blood contains antigen A and antibody B, AB. B group contains antigen B and antibody A. AB group has antigens A and B but no antibodies AB. O group has antibodies A and B, small a and small b, but no antibodies. The mismatching blood transfusion, antibody A of a recipient always reacts with antigen capital A of a donor and causes agglutination. It is of no reaction with the antigen B of the donor. Similarly, we can reverse the case. On the other hand, a small amount of antibody of the transfused blood is not sufficient to agglutinate the RBC of the recipient blood, so it gets dissolved and diluted in the recipient blood soon after transfusion. This is the reason why the recipient's red cells never agglutinate. Thus, in mismatching transfusion, it is always the red corpuscles of the donor blood that agglutinate and not those of the recipient blood. The possibilities of permissive blood transfusion are the following. Then, compatibility of blood transfusion. Since A group contain antigen A and antibody B, there are some difficulties. so it can receive A and O groups. Similarly, O group contains antibodies A and B but no antigen, so it can be donated to all groups. It can receive only O group.